we are going to continue what we've been doing with polynomials and even synthetic division, starting with the factor theorem. This is something that we touched on in the last lesson, but it's just saying that this polynomial x minus k is a factor of f of x only if this should actually say f of k is equal to 0. So there's a typo. Make sure you change that. F of k is equal to 0. That means that the remainder is equal to 0. So for this one, we're going to determine whether or not x plus 4 is a factor of each one of these polynomials. And the way we do that is with synthetic division. Remember that x plus 4 means that k is equal to negative 4. And then when we do our synthetic division, we have 3. There is no x cubed term, so we need a 0. Negative 48, 8, and 32. That 0 right there tells us that yes, x plus 4 is a factor of this polynomial. Let's do it with the next one. We still use negative 4. No. On this one, x plus 4 is not a factor. Another type of problem you're going to see is being asked to take something and factor into its linear factors if something is a 0. So something you need to know about linear factors, x plus 3, that's a linear factor of something. 2x minus 9, linear factor. So we're looking for things that if you graphed them, you would get a line. It tells us that 5 is a 0 of this, so when we set this up, we're actually going to use that information so that we can do our polynomial division. And just so you can see what that looks like, if 5 is a 0, what that means is that x minus 5 equals 0, so x minus 5 is one of the factors, and that also means that k, in this case, is equal to 5 for when we set up our synthetic division. So we set that up. And we know our remainder should be 0. Yes, so that's correct. That means that just like in the last class, f of x is equal to x minus 5 times 6x squared minus 7x minus 3. So now we've got a quadratic polynomial that we can factor. So 6, we'll start with 2x and 3x. Because this is a minus 3, we need a minus and a plus. And then values that multiply to 3, we need 3 and 1. Let's see if that works. 6x squared plus 2x minus 9x, so that's negative 7x minus 3. So the linear factors here are this. You have x minus 5, 2x minus 3, 3x plus 1. First of all, rational zeros theorem. Rational means that it can be put into a fraction. So if we've got some rational number, some fraction, and it's written in lowest terms, and it's a zero of some polynomial that has integer coefficients, big deal, must have integer coefficients, then what we can say is that the numerator is a factor of that constant term, the one with no x on it, and the denominator is a factor of the leading coefficient, which is the very first number. So let's take a look at this one. Here we've got a polynomial. The first thing we're going to do is list any possible rational zeros. So P has to be a factor of 4. Factors of 4 are things like plus or minus 1 and plus or minus 4. Also, plus or minus 2. These are all numbers that you can divide 4 by. Q will be all factors of 8. So that's plus or minus 1, plus or minus 8, plus or minus 2, plus or minus 4. So now we need to start looking at the P over Q. We can have plus or minus 1 over 1, plus or minus 4 over 1, plus or minus 2 over 1. So here I just did all of these each over this term. Now I'll do the same thing over this term. So that gives us plus or minus 1 over 8, plus or minus 4 over 8, which is a half, plus or minus 2 over 8, which is a fourth. Now we will look at all of these terms over 2. Plus or minus 1 over 2, plus or minus 4 over 2, plus or minus 2 over 2. We don't need to repeat these values. Now we'll look over 4, plus or minus 1 over 4, plus or minus 4 over 4, plus or minus 2 over 4. So these are all of the possible rational zeros for this function. From here we have the task of figuring out which one of these possibilities, and there are 12 of them, is actually a zero. Here's where you need to use your trial and error. Start with 1. So we now know that 1 is not a rational zero. Try negative 1. Success. Negative 1 is a zero. So we'll say x plus 1. That's a zero. So now I'm going to divide this one by some other ones until I start figuring out where we are. So we'll take the next one on our list, 4. Ah, that's nice to see. So 4 is also a factor. And now I have a quadratic. And from here, I should be able to factor this quadratic. Eight would be 2 and 4. Looks like I've got a plus and a minus. 1 and 1, does that work? 8x, that's minus 2x plus 4x. That does not work. So I'll go in and erase here. Make that minus and plus 8x plus 2x. Yep, that works. So my linear factors: x plus 1, x minus 4, 2x minus 1, 4x plus 1. So a word of caution. This rational zeros theorem only gives you the possible zeros. You absolutely have to check to determine the actual zeros. The other thing you need to pay attention to is that all the coefficients need to be integers. So take a look at this example. We've got lots of fractional coefficients. What we can do is we can multiply by the common denominator, in this case, 6. When we do, we get a different function, but the zeros of our new function will be exactly the same as the zeros of our old function. Also, if you take a look at this one, you should notice that you can factor a 3 out of every single term. So if you do that, you would again get a new function. Factoring out a 3, you'd get 2x cubed, 11x squared, minus 7x, minus 6. But again, all of the zeros of this new function are exactly the same as the zeros of your old function. So make sure that all of your coefficients are integers. Make sure that you factor out any common factors. As we proceed, we've got the fundamental theorem of algebra. Every single function defined by a polynomial of degree 1, meaning that x is to the power of 1 or greater, has at least one complex zero. That means that every polynomial can be factored, even if the factors you get are not real, if they are complex. You can still do that. The second thing that's important to pay attention to is the number of zeros theorem. Any function that has degree n, meaning that the exponent of your highest value is some number, then you have at most that many distinct zeros. Example, if you have x cubed plus 9x squared plus 6x minus 4, you have at the very most 3 distinct zeros. Okay, so thinking about those last two theorems that we looked at. Find a function defined by a polynomial of degree 3. Degree 3 means that x is going to be cubed, and that's going to be the highest exponent we have that satisfies the given conditions. Our zeros are -3, -2, and 5. That means I've got x plus 3, I've got x plus 2, and I've got x minus 5. That's easy enough. But we have to remember that we could have a constant sitting out here, and we need to know what that constant is. So the way we figure that out is by using this second piece of information. F of -1 is equal to 6. So instead of f of x, I will put 6. I will keep a where it is because it could be there, and in place of every single x, I will put -1. Two times 1 times -6 is -12. So a is equal to -1/2. So my function is equal to -1/2 times x plus 3 times x plus 2 times x minus 5. If you would like to multiply this out, you are welcome to do so, but I think leaving it in factored form is just fine. The next one, it says 4 is a zero of multiplicity 3, and f of 2 equals -4. Now this looks like, oh, I don't really even know what that means. All it means really is that 4 is a triple root. You guys remember doing that from Algebra 2, double roots and triple roots. So if I've got my f of x, and a sits out here because it could be anything, x minus 4 is a factor 3 times. And it tells us f of 2 is -24. So I put -24 in place of f of x, and I put 2 in the place of x. So this would be -8a. And since I don't have room, I'll come up to the side here. I get 3 is equal to a. So f of x is equal to a times x minus 4 cubed.